Now we come to characteristics of first order reactions. Number 1, unit of rate constant K. The unit of a specific reaction rate for a first order reaction is time inverse. Second, the time required to complete a definite fraction of a first order reaction is independent of initial concentration C0 of the reactant. For example, calculation for half change period T half, since K is equal to 2.303 upon T log of C0 upon Ct. So put T half for T and C0 by 2 for Ct. We get T half equal to 2.303 upon K log of C0 upon C0 by 2, or T half is equal to 2.303 upon K log of 2, that amounts to 0.693 upon K. Therefore, T half for a first order reaction is a constant quantity independent of C0. Here you may remember, in general, for any reaction, T half is proportional to C0 to the power 1 minus n, where n is order of reaction. Well, our third characteristic is graphical presentation. Since T is equal to 2.303 upon K log of C0 by Ct, hence if a graph be plotted as shown in the adjoining figure between time T versus log of C0 by Ct, then it must be a straight line passing through origin. Otherwise, we may write T equal to minus sign 2.303 upon K log of Ct plus 2.303 upon K log of C0. According to this, if a graph be plotted between time T versus log of Ct, then it must be a straight line with slope equal to minus 2.303 upon K as shown in the following figure. The fourth characteristic is, if a second order reaction A plus B changing into products be carried out such that one of the reactants is in excess, then it will no longer remain a second order reaction. Rather, it will become a first order reaction with respect to that reactant which is not in excess. Such a reaction is known as pseudo first order reaction. This can be mathematically proved in the following manner. A plus B giving products be a second order reaction, then concentrations are A and B and 0 at time t equal to 0. Then A remains A minus X, B remains B minus X with some concentration of the products at time t. Therefore, we can write dx by dt equal to k into A minus X into B minus X, or integration 0 to X dx upon A minus X into B minus X equal to integration 0 to T k dt. Solving this we get K equal to 2.303 upon T into A minus B log of B into A minus X divided by A into B minus X. Now suppose B is taken in excess so that concentration B is much larger than concentration A. Hence, A and X can be neglected in comparison to B. So we have K equal to 2.303 upon T into minus B log of B into A minus X upon A into B. Considering the concentration B to be almost constant because it is very large, we can write K into B, that's equal to K dash, the new rate constant, and that's equal to 2.303 upon T log A upon A minus X. This represents a first order reaction with respect to the reactant A. Finally, in number 5, we have some examples of first order reactions. A. Decomposition of azoisopropane gas. B. Decomposition of H2O2. C. Decomposition of ammonium nitrate. D. Decomposition of dinitrogen pentoxide. E. All radioactive decays, for example. F. Hydrolysis of sucrose. G. Hydrolysis of an ester, acid catalyzed. The last two are examples of pseudo-unimolecular reactions.